Hello, everyone. Welcome to this first lecture of Fundamentals of Structural Dynamics. Um, as you know, this your participation into this course is voluntary, and I am offering this course because I wanted to give back to humanity, and I strongly believe in giving back to people, and because um, I feel that I have been privileged to learn certain stuff, and not everyone had the same opportunity. I intend to eventually make all of this material that I upload uh, freely accessible people, for all people of all races and religion, without any differentiation. Um, a few things before we start with this first lecture. I would be uploading the course material on uh, the Google coursework website. The link to the course website will be emailed to everyone who has paid up the subscription fee or has approached me for exemption of the registration fee. If you have not paid up for the registration fee or have not asked me for the exemption, I assume that you were initially interested in this course but are eventually not that interested anymore, and we will not be bothering you with the intimation and the notifications and all that for this course. Secondly, the format of this course will be a little different. I'm offering this for practicing engineers, and because your participation into this course is voluntary, I will assume that the onus of learning is on you. Um, I'm amazed that most of the engineers out there do not even know the fundamentals of structural dynamics, and this is, I think it would be fair to say that this is at least 50% of whatever we engineers actually practice out there. So, with this, let me start with this first lecture, and the purpose of this lecture is to um, basically demonstrate to you guys as to how significant the subject of structural dynamics is for us structural engineers. So, if I ask you to evaluate the axial force in the columns, the bending moment and the shear force in the beams and the columns, and the flexural moments in the slab, that's not a problem for most of you. And that's because we spend all of our undergraduate, trying to learn different methods as to how to evaluate these force effects in the structural components. So that's a no-brainer, classes, right? But the fact is that the real world is full of forces that impart dynamic loads on the structures. Two of these examples are shown on this slide. On your left, we have a tall structure that is subjected to wind load, and whereas most of us apply wind load as a pseudostatic load, as a pseudostatic lateral load for low rise, mid rise, and even higher buildings, the fact is that for tall buildings, the wind load induces um, vibrations, lateral vibrations in the building, and due to a phenomenon known as vortex shedding. Similarly, for long span bridges, wind-induced vibrations are critical. Now, to understand the effect of these dynamic loads on the structure, we have to understand the dynamic properties of the structure itself. Then, even for low-rise and mid-rise buildings, there are loads on these buildings which introduce vibrations. So, for example, one of the key considerations for design of a building is that a person walking on the floor should not cause disturbance to the people underneath and around him. And this is actually the typical problem that most structural engineers consider while designing flooring systems. And we have to consider, the floor vibration analysis has to be carried out before we can satisfy ourselves regarding certain configuration of the floors. Similarly, MEP equipment, it's has a lot of rotating parts in it, and it introduces a lot of vibrations in the structure. Now, this mechanical equipment has to be placed somewhere, and more often than not, this mechanical equipment is placed on the roofs of a lot of buildings, and proper consideration has to be taken into account to isolate the roofs from vibration of the mechanical equipment. And these and on this picture you can see that base isolators are installed at the bottom of this MEP equipment, and but you need to understand as to what stiffness of and what damping characteristics should these insulators, base isolators have vis-a-vis the vibration characteristics of the mechanical equipment. Then we are all familiar with the structural dynamic scenario that most of us most commonly have to encounter, and that is due to earthquakes. The phenomena is that a fault ruptures somewhere in the earth crust or deeper, and the disturbance travels through the soil medium and reaches your structure. So the dynamic behavior, the dynamic response of your structure is not only dependent on the dynamic properties of the structure itself, but is also dependent on the dynamic properties of the soil on which the structure has been constructed. Also, one of the relatively less recognized applications of concepts of structural dynamics is in structural health monitoring and testing. We have equipment that record different parameters of the structure, including structural vibrations that are induced, and these vibrations are then analyzed to assess the state of the health of the structure and as to if there is a need for repair or retrofitting. Still, other applications of structural dynamic concepts is in dynamic pile load testing, in structural integrity testing of the piles, and in pulse velocity test of concrete. On the picture, in the top left of the, you can see a hammer of a certain weight that is raised a certain height above the head of the pile. The hammer is dropped on the head of the pile through a certain distance, which imparts a certain blow. This blow causes a compressive wave that travels from the head of the pile to the toe and then bounces back. This passage of wave along the length of the pile is analyzed along with the permanent settlement, to assess the axial pile load capacity of their particular pile. Then, once piles have been cast, there can be a lot of defects, and some of the defects are shown in the picture here. And you know, there is a small hammer that is used to cause a small amount of compressive waves. Those compressive waves travel from the head of the pile to the toe and bounce back. There is a receiver at the top of the pile. The compressive waves are then analyzed to assess as to if there are defects in the pile, such as necking, bulging, or if there are fractures along the length of the pile. Also, we structural engineers are much more familiar with the concept of ordering pulse velocity tests to check the integrity of the concrete. Basically, what this test is, it causes waves to pass through concrete, and if there is a fracture along the way, the waves bounce back, and we tend to, basically, we can get an estimate of the degree of fracture and the degree of damage to concrete. Regarding course objectives, the first course objective is to learn the basic theory in linear analysis of structures subjected to time-dependent loads. The linear analysis of structures is a key term here, and there is a step further where we do the time dynamic analysis of nonlinear structures, but that is not what we are going to talk about in this course. The second objective is to understand the basic physical phenomena of vibration of structures. The third objective is to be able to understand the computational results for structural dynamic software. Now, this is very useful for all those practitioners out there. We use ETABS or other softwares to carry out structural dynamic analysis of different projects without even understanding what is the basic behind those algorithms that we use. Uh, so one of the key objectives here would be to understand as to, for example, what are the Ritz vectors, and why are they useful, and under what scenario, for example, should we use them. Then what are direct numerical integration schemes, and what do we have to do if the code is not converging after we have used it with P delta effects, for example, for very tall buildings. So you get to know all of those things only after you understand the fundamentals of the theory behind structural dynamics, and that is a certain degree of pain that you have to take. And the last objective would be to enable basic understanding of common applications of dynamic concept. Regarding prerequisites, assume that you are able to do direct stiffness. You're familiar with the direct stiffness approach. You are able to calculate force effects due to static loads. Reading material, it's a very famous book, Theory and Application of Earthquake Engineering by Chopra, Dynamics of Structures, Theory and Applications of Earthquake Engineering. The Bible of structural dynamics is Dynamics of Structures by Claw and Penzin. Claw and Penzin were actually the teachers of Professor Chopra, and they're considered as one of the pioneers of many of the different concepts that we currently use to analyze structures for dynamic force effects. Other reference materials, if you would like, Structural Dynamics Theory and Computations by Paz, Dynamics of Structures by Hammer, and Engineering Vibrations by Inman. So, so here is a tentative timeline, and along with the topics that we are going to cover during this course. Now, when I was at Stanford, we used to cover all of this material within 8 weeks or 9 weeks, and we also used to have a midterm and a final. But I have deliberately stretched the timelines because I understand that most of you are practitioners, and you guys have a busy life, and I would like to give you a reasonable amount of time to catch up with the course material. And this is a relatively lax time table. I will try and to finish this course within the 24-week mark. Uh, I would like to advise all of you to be regular in engaging yourself with the material of the course, because what tends to happen is if you are too um, transient, if you're too tangential when it comes to engagement with the material of the course, you tend to lose focus, and that's where I don't want you guys to be at. And this is to if you take my advice, this is a really fundamental um, set of concepts that every structural engineer should know. I mean, you won't be able to understand earthquake engineering without understanding these concepts, and so without that, you won't be able to practice in many of the areas of the world, because there are many places and many big cities are located near, um, in seismically active zones. So that's a big sort of constraint to have as a structural engineer. I would be uploading the course like videos on Mondays mostly, and I would be holding a couple of hours of office hours on Saturdays. That should give you 3 or 4 days to go through the stuff and compile a set of questions. On Saturdays, I would be holding office hours through Zoom, where most of you guys would be able to directly interact with me, ask me questions. I will be uploading assignments using Google Coursework website. It will be up to you to go through the assignments, and I will also be uploading the solutions. If you don't work on the assignment problems, I would be disappointed, and I would strongly suggest that you do, because applying your concepts to numerical problems will cement those concepts in you, and by associating, your ability to do so. So with this, I will be uploading another lecture coming Monday. I wish you guys all the best. And meanwhile, if you have any questions, do approach me with your emails, which you already have with you guys.